Hey, for those of you online, thank you for attending online. We're here today with our speaker from our very own RAL, who joins us recently in August of this year. This is Dr. Jacob Stuyvenvold-Ellen, who's a project scientist. He comes to us originally from Yale, where he did his postdoc appointment in the Department of Earth and Planetary Sciences there. And prior to that, he got his PhD in climate science at Utah State University, where his family's from. And there he was studying the impacts of changing Pacific on North American drought, atmospheric rivers, and explosive cyclones. And prior to that, he got his bachelor's in 2016 at Loyola Marymount University in Environmental Science. So today, he'll talk about a very exciting topic related to work he's been doing in recent years, and very pleased to turn the mic over to you.
Thank you. Yeah, really appreciate it, Chris. Today I'm going to talk about kind of extreme phenomena that happen in an entire ocean basin apart, and that is fire weather or extreme weather in North America, and then these tropical cyclones that transition into extratropical cyclones over in the western North Pacific. Just want to highlight that I'm here to work on an accordex. So I'm working with Rachel McCrary and Truda Eidhammer and Seth McGinnis on downscaling CMIP6 GCMs over North America using WRF and MPAS. So this is what I've been doing for the last 3 months, and I'm very thankful to those who have helped me configure and run WRF thus far, because I've asked quite a lot of questions and I haven't done this before. But when I give these talks, it always makes me I have a bit of an existential crisis, because I think about what kind of scientist I am. I've worked on quite a variety of topics, from how climate and water influence cannabis cultivation in Northern California, explosive cyclones in the North Atlantic, the topic I'll talk about today, atmospheric rivers, fire weather in Nepal, and my postdoc was all on ENSO and global climate dynamics. So I don't really know, there's not like a consistent through line between a lot of this work, and I've done a lot of different things. And because it's been getting cold, I'm starting to make a lot of stews and soups. And I've thought that if my cumulative scientific experience was a soup, it wouldn't be a very tasty one. All of these ingredients by themselves might be nice in certain contexts, but if you shove them all together, it doesn't really make for a nice talk. So today, I'm just going to, rather than try and consolidate all this into a big topic, I'm going to just try and tell a nice story about some extreme events that happened in 2020 over Labor Day. And first, we'll start with a bit of a case study, looking at these Labor Day fires over the Pacific Northwest. I'll go through just a quick introduction. We'll talk about the synoptic overview of this event. We'll look at some dynamics of typhoon jet interactions, because these are really fascinating. And then finally, we'll end with model diagnostics. At the time, I could not run atmospheric models, so we found a kind of interesting way to use a forecasting system to help with our research. I also want to highlight that we probably have mixed relationships with media at this point, but I got an opportunity to write this scientific journalism piece with a professor in journalism at Utah State. And we're going to try and tell some of this story through the lens of people that we interviewed and talked to that were impacted by the fires. So we'll have Nancy Beam helping us out today, who is a resident of Blue River, Oregon. And yeah, if you're interested in reading this, it's in the Eugene Weekly. There's probably some holes and gaps, but overall, I think it's quite a good example of scientific journalism. All right. So Nancy Beam. It began as a tempest the likes of which she had never felt in more than 70 years of living in Blue River, Oregon. East winds are always a little spooky. I could hear trees and branches cracking, breaking, falling. The storm was somehow soothing though, and Beam fell asleep. So at midnight, Beam woke to a call from her grandson. There's a fire at Holiday Farm, he told her. You need to evacuate. Holiday Farm was up Highway 126 miles away. Okay, so why was Nancy Beam running? Well, on September 8th, you can see from this Goes West satellite animation, we had fires. You can see the embers of them burning as the animation turns from day to night. Really strong and large fires over the Pacific Northwest. and really strong easterly wind event blowing all of this smoke and plume out into the Pacific. But when she walked outside and scanned the ridge, the sky was orange. It had been a couple of years since I had done any running, she says, but oh boy, I definitely remembered how to do it. So if we zoom out and take a little bit of a look at the synoptic situation over Western North America, we're just using ERA5 reanalysis and looking at geopotential height. And you can see we have a nice big ridge over the west coast and a trough kind of digging in to the Intermountain West. If we zoom out even a little bit farther, we get a pretty characteristic omega block that was featured right over, the west coast of North America. And importantly, there's a feature of Rossby wave breaking. So in this low pressure system cutting down over North America, you can see that it's kind of folding over on itself. And Rossby wave breaking events, as we know, are strongly associated with extreme weather outbreaks for much of the US. You can take a little bit closer look. So I've got the easterly winds plotted in this box averaged region over Oregon and Northern California. The x-axis here is time. So we're looking from the beginning of August through the end of September, and the y-axis is just meters per second. The gray lines here denote all of the wind, the daily wind from ERA5 for 1979 through 2019. And then this red line here is 2020. So you can see that things were progressing quite normally in 2020 until about September 8th with this really strong easterly wind outbreak. And it's about the strongest that it's been in ERA5. Obviously, we would need some station data to confirm that, but very strong easterly winds. And the reason that Nancy Beam, someone who's lived in Blue River, has known that these are really dangerous is because of the topography of the western United States. I don't probably need to convince you all about the role that dry downsloping winds can play in facilitating fire outbreaks, but they're really important. And just to give you a sense of how quickly these fires expanded and burned through much of this region, we can look at a time series. This is a daily time series of cumulative fires burned. The y-axis is the hectares burned, and then the x-axis, it's days and then September. It's confusing for my brain, but you can see that there were a few fires already burning, quite small, especially the Lion's Head one. And then on the 8th of September, there was a very rapid outbreak. About 300,000 hectares were burned in a 48-hour period. So quite a lot of fires spawned and burned up through September 8th and the 9th. To figure out why this really happened and what set up this synoptic situation over Western North America, you do have to go back and look about 12 days. So Typhoon Bavi, Maisak, and Haishin, 12 days before this fire outbreak, had translated up into the Korean peninsula, made landfall, and transitioned into extratropical low pressure system. So I'll just refer to these as transitioning tropical cyclones or ETCs. I don't know, I might say a lot of different things. I might call them typhoons, but these are tropical cyclones that had made landfall in Korea in quick succession. And part of the reason I think that we were connecting these two events, there's been a lot of literature connecting how typhoons can influence downstream weather extremes, but I had my advisor who was coming back from Korea at the time, and I imagine he had quite a very turbulent flight, and he landed in the western United States at about the time that the fires were outbreaking. So when he landed, we had talked and gone over the situation and decided to look a little bit more into it. So just to give you a freeze frame, on September 8th, you can see this Rossby wave train translating across the North Pacific, resulting in that omega block over Western North America. And while there were fires in the Pacific Northwest, it's also important to call out that there were a lot of extreme weather events in the Intermountain West as well. I think Denver got like 6 inches of snow or something. Salt Lake City had hurricane force winds, and they toppled a lot of the oldest trees in the city. So there was quite widespread impacts from this Rossby wave breaking event. Let's talk a little bit just about how a typhoon can cause this downstream response and this Rossby wave amplification. So Julia Keller has a really nice review paper, and she touches on and makes this nice diagram of these idealized studies done by Reimer and Jones in 2007. And what they did is they basically took an idealized mid-latitude flow, and they pushed a tropical cyclone into it in this idealized setting. And they quantified how the different components of a tropical cyclone can contribute to this initial ridge amplification. So we're using the potential vorticity framework here because it's quite helpful. And the steps towards really triggering a downstream response start with the fact that the transitioning cyclone tightens the jet's potential vorticity gradient. So that's contributed by the advection from anticyclonic and cyclonic circulation, and largely by this divergent flow. So you can see these green arrows here as well. And those are denoting the diabatic outflow from a tropical cyclone, which is all of the latent heat that's generated within the storm and deposited into the upper layers of the atmosphere. So yeah, these tropical cyclones can trigger this local ridge amplification. And the next important step is really a jet streak. When that potential vorticity gradient tightens, the jet stream speeds up, contributes to ridge amplification, and begins the process of forming a downstream wave. There's another nice diagram in this paper, in this review paper, showing the whole picture, and you can see the transitioning cyclone here. The orange is denoting the jet streak formation, and you can see the Rossby wave propagation coming from that. And this has been shown to have a whole lot of impacts on predictability of downstream weather. This really hampers our ability to predict what kind of weather we're going to experience in the coming days over North America. There's also a lot of really interesting dynamics with this preconditioning part. So whether the storm is coming up into an approaching trough or an approaching ridge can really impact what this looks like. It's quite a complicated thing, but in general, this is the nice schematic that gives us a sense of what happens under optimal conditions. So after having those schematics, we can take a look at what was going on. This is 12Z of September 3rd. So that's 5 days before the big fire outbreak. We're looking at Typhoon Mysak, and I'm broadly showing where this storm is and where its transitioning elements are as this omega. So this is indicating we have rising air associated with Typhoon Mysak as it's transitioning into an extratropical storm. We have the PV gradient showing the jet stream. So I'm showing 2, 4, and 5 potential vorticity units, which are generally kind of highlighting where the jet stream is. And you can see that this storm really kind of dramatically has created this local ridge over Eastern Asia, with the negative potential vorticity advection being the primary dynamic cause of that, or at least a useful diagnostic for showing it. So yeah, this storm is really amplifying the local ridge in a very kind of textbook sense when you look at typhoon and jet interactions. We're going to do something a little weird. I considered that hour 0, and I'm showing different variables over different times in this plot. So this is about 12 hours to 24 hours after that first plot that I showed you. So the MSLP is just the mean sea level pressure highlighting where Typhoon Mysak was at hour 0. And you can see this 12 hours later, we started to form this really strong jet streak. So this is upper level zonal wind at about 250 hectopascals. And you could see that really important process of downstream Rossby wave amplification starting. And then importantly, you can also see about a day later, we're starting to form and deepen an extratropical low pressure system over the North Pacific. Okay, and if we go 108 hours later, so now we're about 4 or 5 days later, you can see the ridge and the omega block that ended up amplifying these wind conditions for the conflagration that happened on September 8th. So all of this kind of translated into creating the synoptic condition on the 8th of September. I think we showed the impacts of the other storms as well in this paper, but one thing that we initially thought of was like, well, we don't really know how important the impact of the typhoons was without modeling, right? We have a sample size of 1 by looking in reanalysis. So when we were thinking about the impact of the typhoons, well, we wanted to figure out how we could simulate a different scenario in which the typhoons weren't there. In 2020, though, running a high-resolution regional model was not a part of my toolbox, so we thought of a way to use the GEFs, and this has been done, I think, a few times before, but it was really nice because, one, I didn't have to learn how to run WRF. We had all of this publicly and freely available data out to 16 days. It's initialized every 6 hours with 21 ensemble members, so really what this meant was, for an unskilled graduate student, this was a huge increase in our sample size. And I got to tell this joke anytime I consider sample size with climate scientists, but we're very used to sitting down at the sample size bar, right? It's something we're constantly considering and thinking of. And we often find the Earth there. Unfortunately, it's really only capable of having one drink. This is why we've made good friends with models, which can really take quite a lot. And if you get really lucky, it might even have a good sense of what the future looks like. So these are pretty awesome. We also know that they have their deficiencies, right? So this application of the GEFs isn't necessarily perfect, but it was useful for what we needed it for. Okay. So yeah, in thinking about this, would the fires have happened without the typhoons? The first step we took was to group ensemble members of the GEFs. I'm going to show you, this is the observed target mean sea level pressure fields for the 3 tropical cyclones. We've got Bavi in the top, Maisek in the middle, and Haishan all occurring at relatively different dates. So the 27th of August, September 3rd, and August 6th, 3 days later. We found the forecast members. There's over 100 ensembles in this group. We found the forecast members that accurately captured the typhoons. I was just using a simple spatial correlation. And you can see that the over 100 ensemble members, which did a good job of simulating these typhoons, are doing a really good job of simulating not just the spatial location of where the storm is, but also its intensity. So yeah, just you can compare the mean sea level pressure fields and see that they're quite similar in this group. I then found the ensemble members that were not capturing these typhoons. And to convince you that it did a decent job, again, this is over 100 ensemble members, and the mean sea level pressure field, you can see that the typhoon seems completely absent. So this mean sea level pressure low associated with it just is not present in this group. And the rest is really quite simple. So now that we have these 2 groups, one with the impact of the typhoons and its subsequent downstream development and one without it, we can just look at the circulation fields and see how well they captured this omega block and this amplified Rossby wave breaking event over the western US. Okay, so this first plot, I'm just showing Typhoon Maisak because another finding is really that even though there were 3 typhoons, it was the second one that had the biggest impact. The timing of it and its phasing with the approaching upstream trough led to a really resonant reaction downstream, which was probably ultimately the main driver of amplifying mid-latitude circulation. The red lines here are the ensemble members with the typhoon. The black lines are the ensemble members without the typhoon, and you can see that the circulation is quite zonal. We do have a little bit of ridging in the without typhoon groups, but it's much less amplified than compared to observations, which we can see in the dotted gray line. When we also add in the impact of Typhoon Haishan, by including all of the members that also captured that storm, we get a really good agreement with reanalysis. So again, the red lines here are showing us the group with the typhoon, and generally things match up, especially over West North America, quite well. We're not capturing this Rossby wave breaking as well, but I imagine some of the ensemble members are doing a good job of picking that up and others aren't. So the answer, would the fires have happened without the typhoons? Well, yes, some of the fires were already burning, but the meteorological conditions that really stoked and spread the fires were strongly amplified by typhoons an entire ocean away. So back to Nancy Beam. The heat was surprising, she recalls, but the wind was astonishing. It was creating all these sparks, blowing smoke, blowing debris this way and that, she says. If you've ever started a fire with bellows, you know what a difference it makes. That's exactly what it was like. That's what the wind was doing. So what this all means, I think, typhoons, destructive weather events themselves, there were a lot of impacts from these 3 tropical cyclones over Korea as well. They can and do amplify fire weather conditions in the western United States. This has been shown a little bit for cold weather outbreaks or other extreme events like I just talked about with Chris. But yeah, I think this is one of the first cases showing that it can happen with fire weather. I do think we missed a few things with this study. I was very fresh. This was my 3rd semester of graduate school. So while it's interesting, and I do find it very interesting, I don't think these results really help us prepare for similar events. And something that I've thought about and would really like to do at NCAR, an interesting way of, it doesn't have to be with this case study, but of looking at other case studies, is this ensemble boosting technique. So Eric Fisher, who is I believe he's at Zurich, has this really nice paper where he looks at the possibilities of something like a Pacific Northwest heat wave. So the y-axis here is temperature anomalies for a box average region over the Pacific Northwest. And on the x-axis, again, we're just looking at time, June through July. And what they do is they find an event of interest and they gain some initial conditions from that time. They perturb those initial conditions with tiny temperature perturbations and run many short ensembles. The cool thing is that what you get is this estimated range of possibilities. People have often referred to this as storylines, and y'all are probably very familiar with this. But I think it's a cool way of getting to this question of how extreme can something get, or how likely was this event happening. You can dive into predictability. So this is something that with those GEF's ensemble members we could have looked at, and I wish that we would have. Okay. So about a year later, we wanted to rethink about how to approach this problem. We had shown a case study, but I think I was very interested in extending this to more of a climatology and trying to think about, well, how often does this happen? So I'll talk about this. We'll go from a case study to a climatology, and I'll summarize some of these results. And then I'll focus, these last two bits are a little bit things that I've been thinking of doing now. That we have a little bit. I'll show you the results from the climatology are a little lackluster, to be honest. So I think there's another way to think about this problem, and I'll highlight that at the end. Don't worry, part 2 is shorter. I just love this meme. Okay. So enough with the case study. Now we're looking at a climatology of a few different things. We have the typhoon track density first. I've interpolated this onto a 2x2 degree grid. And what you can see is that typhoons are occurring in so many different places, right? We have these tropical cyclones. They're occurring over a large swath of the western North Pacific, and each of them have very different, even though the main point that the predominant point that they are found is near Taiwan, they can occur at very different latitudes and longitudes. I'm also showing you the mean zonal wind at 250 hectopascals to try to kind of highlight the jet stream. And I'm showing this for July and August as well as September and October because we have very different jet stream configurations. It's getting much stronger as we move into September and October. And this is a really important ingredient in how a typhoon or how a tropical cyclone can impact and interact with the jet stream. And really the interesting thing here, I guess, is that peak fire season overlaps with peak tropical cyclone season in the western North Pacific. So we thought that there might be some consistent impacts. I do want to highlight, though, that, of course, every tropical cyclone is a very, very different storm. And not only is the storm quite different, but, yeah, go ahead.
Sorry if I missed it, but what years were the climatology?
Oh, no, that's good. It's 1979 to 2020. Oh. It's not on here. Yeah, so I'm using IB tracks and ERA 5. So again, the idea was like, well, we have this one case study, but what happened for all storms on record? So we can go through and we can find all of these tropical cyclones. It's quite simple with provided data. I'm just showing this red line is tracking some of the tropical cyclones that spun up from July 21st through August 27th in 2000. We can find all those storms. That's quite simple because somebody else has done it. We can group them into similar lat-long positions and type, which is quite nice. They even have categories for storms that made an extratropical transition. So really all of this work was made quite simple. And all we have to do is compare the average response of North American fire weather to different groups of typhoons. So our thought was that, for a given location in North America, if you have a tropical cyclone in a given location, you might be able to see a discernible impact on the fire weather that you experience in that spot. And this is motivated by, even though, of course, tropical cyclone predictability is really difficult, but this cone of probability in the sense of a basin scale is quite good, right? We were hoping that maybe having a sense of where the tropical cyclone would be could give us insight onto where these downstream impacts would happen. Because again, forecast models really struggle to predict the downstream response. And of course, for another location in North America, you might get a decrease in fire weather. It's not always going to be an increase. So I'm going to show you, this isn't the perfect way of doing this, but we wanted to show what the change in fire weather due to these impacts might be. So I've composited 10-day periods where there were not any extratropically transitioning tropical cyclones in the western North Pacific. And I've composited the fire weather and the circulation anomalies over North America for those events. I'm showing you anomalies, so these are differences from the climatology for those same respective periods. And you can see that, there's not much going on in this control. There's not really any difference or significant difference from climatology. But if you put in the group with tropical cyclones, so these are fire weather anomalies and upper level circulation for 5-day periods after a tropical cyclone makes a transition, you can see that we have much more amplified flow over North America, and there are some significantly different or significant deviations of fire weather from the climatology. It's quite messy. I'm not going to pretend that this looks clean or super sensible. And this question that we really posed, is there a consistent response to certain TCs? I can tell you the answer is really no. The strong jet interaction, we tried a bunch of different things to try and figure out whether there was a consistent response we could tease out of the observed data. One of those was strong jet interaction versus weak jet interaction. One was comparing the radius of 30-knot winds, large versus small. One was comparing typhoons which recurve in regions in different locations. And finally, typhoons which re-intensify as extratropical lows versus those that weaken. And just to summarize this paper, I really think it was kind of like, no, you can't predict what the downstream impact will be based off of typhoon characteristics. And I think this is indicative of, a lot of the work has already shown that, well, the mid-latitude circulation is so important for how this response translates to North America. So we have a really small signal to noise ratio here. Because subsetting already a small set of storms is really just not giving us enough information to tease out any impacts. So there's a whole paper on that, which is quite honestly quite boring. But I think the new idea I have is that I've worked on a little bit, but I haven't had the time to finish up, is that fire weather is kind of this complex combination of lots of different variables. You have winds and humidity and temperature and rain and soil moisture, so it's a little bit complicated. So it might be better to look at very simple things like temperature and precipitation, and rather than focusing on the entire distribution, thinking about what's going on the tails. One diagnostic I'm going to describe just to kind of highlight this work is the meridional flow index, and it's just a simple area average over Latin lawn over a jet stream region. So you can imagine 30 degrees north to 60 degrees north, and you just take the absolute value of meridional velocities. So for a meridional flow index that was close to 0, you would expect quite zonal flow. But for something much greater than 0, this would indicate that, well, you have quite a wavy jet stream. And again, we're going to just composite and look at the meridional flow index following typhoons which make an extratropical transition. So you can get a sense of what that might look like on this timeline, where these red periods, these red blocked periods, are the chunks of time that we're compositing to look at their circulation impacts. And again, I'm using ERA 5 from 1979 and the IB tracks data. Okay. So what you can see on the x-axis, we have days relative to the transition time of the storm. On the y-axis, we have the meridional flow index. So this 0 line on the y-axis is indicating the climatology. So any deviations from this would say that, well, the flow index was amplified compared to what is normal for this time period. The dark blue line here, or black, is the North Pacific meridional flow index. So it's a box average over the North Pacific. And you can see that the flow starts to amplify even before the extratropical transition. And it stays amplified for up to 6 days. Maybe even longer. We're showing higher values than climatology up to 10, but there's a good amount of spread, as you can see by these dotted lines. I've also done a box of the meridional flow index over North America. So sensibly, you see that first the North Pacific flow amplifies up to day 2, and then about at day 4 is when the peak of that amplified circulation over North America happens. And this is kind of nice because it's reducing the spatial, if we took a spatial map, it's allowing, it would smear some of the impacts of the composites, but this is allowing us to just look at how amplified is the flow. So about day 4 is when we would expect to see the strongest impacts in North America. And I can also look at the spatial average to show that there is a seemingly sensible pattern here we can see this Rossby wave train amplification. This is a composite of 500 hectopascal geopotential height following tropical cyclones. And you can see this Rossby wave amplification promoting a strong ridge over Western North America and a deep trough over the northeast part of the continent in Greenland. So sensible with some of the features that we've seen from the case study. And what I'm going to show is rather than looking just at the mean distribution, I'm curious about how the extremes might be varying. So we'll define this probability as a probability of surpassing the 95th percentile. I'm going to look at temperature, max temperature first. And we can consider a change in probability or a delta P, just as this, the probability of surpassing the 95th percentile after a tropical cyclone minus the probability when there isn't and has not been a tropical cyclone for 10 days. And what you can see, it lines up pretty well with that circulation feature that we saw. The red is telling us that, well, it's more likely for max temperature to exceed, or it's more likely to have a, how do I say this? The probability of exceeding the 95th percentile is higher for the extratropical transitioning group, the cyclones that have undergone an extratropical transition. So for Alaska, for the coast of Alaska, and for some of these high latitudes, this is saying that, well, when there's a tropical cyclone in the western North Pacific, it's more likely for them to experience a heat extreme. This is also the case for the southeast a little bit. And then this decrease in the Great Lakes, this is really a well-documented feature. This is much like the cold air outbreaks that I described earlier. And we can show that more clearly by looking at minimum temperature. So again, this is saying that, well, when we have a tropical cyclone that makes a transition in the western North Pacific, it is likely 4 days later, more likely to experience a minimum temperature extreme for much of the Great Lakes and eastern region. Nice. Okay, so things I really hope I communicated well today was that, well, from 2020, the Labor Day fires in Oregon were fanned by a strong pressure gradient, ultimately linked to the upstream impacts of typhoons. So this is a good example of compound extremes, right? Oftentimes what we're experiencing in one location has been translated or impacted by something going on somewhere else, which is just a really fascinating thing in the weather and climate system. And then part two, even though this is preliminary, I think the impact of recurring typhoons is so varied. So it's really hard to nail down how these storms are impacting extreme weather in North America. But there are regions that have a measurable risk for things like extreme temperature or precipitation. I want to end with just, I'm really grateful to be at NCAR. I've talked about soup a lot today, probably too much today. But hopefully in the next couple of years, I can kind of curate a more tasty and sensible collection of different types of soup. So one of my favorites, gumbo, I think could be equated to something like actionable climate science, right? This is something I would like to be able to do. And it's hard to do right, but it's oh so good with the proper care. Another kind of soup I'd like to curate is this curried chickpea stew, and I would think this is somewhat like climate and weather dynamics. It's a little spicy and maybe not for everyone, but it's a really fundamental flavor. And finally, climate services. So something I'm really happy to work on and develop at NCAR is climate services. And this is just, your standard chicken noodle, wholesome, filling, rejuvenating, everything you want. Shameless solicitation, right? I put Jacob's stews here, but I'm recognizing that this will be in collaboration with many. Oh.
Online, we have a fire alarm. So if you're still online and you're still paying attention, we just had a fire alarm. Perfect timing. And if you're still paying attention, feel free to ask questions in Slido. Our speaker is still here. Otherwise, we will wrap it up.
You can email me too.
Also, yeah, please do email and keep in touch with Jacob here. Lots of good collaboration opportunities.
Rachel McCreary's online.
All right.
Thanks, folks.
Thank you, sir.
Thank you.
Yep.